Right. So I think I'll start our meeting. Welcome to ASEG's webinar series. I'm the host for this particular one. I'm from Western Australia. I'm the WA branch president there, and I'm hosting a talk, however, for someone who's way over on the east side of Australia. So this is we'll call it a very global Australian geophysics talk. Anandaroop Ray, he's in Geoscience Australia, and his talk is going to be on FWI, on a probabilistic seismic FWI particular talk. So before we get into that, no, I've got to do some housekeeping. That's an important part of being the MC or host. And so we'll start off. And the first thing I like to do would be, of course, thank our corporate members. Now, these corporate plus ones are really, you can consider them, they're literally members more than just sponsors. They help support the entire ASEG, all the way from, Western Australia to Tasmania. And so we've got High Size, Total Seismic, Bell Size. These three are really very helpful for us. And they're, they've made this webinar, just that much more possible. We also have some great corporate members, Archimedes, GDD, Santos, and Southern Geoscience. All these are people that we really would like to thank, especially during, times like these where we can still continue on our communications. Now, I would in particular like to thank the WA sponsors. You see, we've got a few here. I'm not going to go through their names, but they have really been very helpful for our organization here in WA. But there are quite a few in South Australia and Northern Territories, as we can see, and New South Wales. All of these people make what's happening today possible. Okay. So with that, I can go on and start talking a little bit of what we're trying to do here. Now, because we've got, it's pretty great, let me go up and check. We've got 61 participants. So you can imagine if you were not, if you were not muted and you had your own little videos and stuff, we would swamp this thing and make a mess. So let's just make sure that when you have any questions, which you should have, hopefully, or you have problems, type into that Q&A little button down below that you'll see on your screen, and that will allow you to, and we'll be able to see it. So myself and Anand will be able to see that, and if you have problems with the talk, clarity or something, we can try to address some of that. The good thing is we are recording this talk, and that'll come out in just a few days actually on YouTube. So if you missed something or you wanted to go over something, we'll have that for eternity. Right, so let me go through. We have, this is just a partial list of what's coming up for ASEG. So we've got a bunch of pretty neat webinars coming up here. So first one by Claire Millard is, I would call it Solid Earth Geophysics. We've got mantle dynamics, tectonics, and so it's going to be neat. And for sure, I'm going to try to check that out myself. Sumit Verma from University of Texas is going to give us an Australian SEG talk, which is pretty neat. And that is going to be using seismic attributes to try to look at fault networks analyses in the North Slope. So that should be pretty fun. I actually, in my previous history, did a lot of work up there, and that should be a pretty wild thing to take a look at. The next one is more of an evening one, and that's by Dr. Arnetz and Cesaro. And I guess I'm just not aware of what that is, but 10 years in the wild, the P223 experiment. It sounds pretty cool. I'm assuming that there's going to be a lot of beard growth and stuff like that if it's actually out there in a while, but it should be fun. And then Marina Costello, that looks like a very appropriate kind of a talk, mentoring through change perspective. I mean, in these times that we have, I think that could be a really neat talk for all of us to listen to. And lastly, in this little grouping, we've got Anandaroop Ray, who's talking about computation methods in geophysics. Right. So now we'll go back to more of an advertisement for ASEG. So here are the member benefits that we have. I mean, I'm sure a lot of you know these, but I'm going to go through them as I should. So we have access to our own technical journal, which is pretty neat. And but we also have preview, which is kind of a you know, a day-by-day kind of topics in geophysics in Australia. And when the conferences are open, which may or may not happen sooner or later, we do get a nice reduced entry to the Australian conferences. And of course, you probably all know that we do get free entry into any technical events like our tech nights here in WA. And the annual wine offer, I have taken advantage of that before. I got some very good wine at a good price. And of course, we do have social events besides just the technical events in each of the states. The next item I really like, you know, it's professional networking. What I really like about ASEG is I think it's kind of unique in these kinds of organizations. It's not just like a one-sided kind of organization, you know, like it's not oil and gas or mining and minerals. It's both, and it mixes in with the uni and the you know, earth geophysics that we come through. So we have near surface geophysics, we've got deep earth and archaeology, everything like that. So it's a way that there's a good cross-cultural connection. So if you pay attention to what's going on, you can learn a lot and see what others are doing in our technology. So that's actually the main reason why I volunteered for ASEG for this, because of that kind of call it multicultural type thing. Now, we also do research funding, and we've already given out some awards there, and travel scholarships for students. Now, WA, just an update there, we've extended one more time, we've extended the application deadline through the end of August, you know, and so hopefully, and that's because of the COVID, there's not that much communication, you know, without face-to-face, et cetera. It's more difficult for the students to even know it's there. So I'm hoping if anybody's listening, you can pass that information to anybody that might be keen to go to an AEGC conference next year if it's coming up. And the other neat thing, which is pretty unusual, we actually have a free membership for students. That's pretty rare. You know, you can have discounts, but we actually have free memberships. So one more thing that I'll talk about here, it's not really member benefits, but because we're now in WA, we're in lockdown. We're now in number 3 in terms of the get out cards. And that means that we really can be allowed to give our face-to-face tech nights again, if, you know, with care. So we may be starting up pretty soon with those. We'll keep you informed. And in terms of keep you informed, this is how we do it. We've got email newsletters. We've got our website, of course, Facebook, Twitter, LinkedIn, and as we mentioned, it's really cool. Most of the webinars that we're doing, and even some of the local ones, we put them out on an ASEG list out there on YouTube. And this one will be out there pretty soon, you know, early next week. So, but others are out there already, and they can be, so if you miss them, it's something you can take a look at. Okay, so with that, I'm pretty much almost, you can be happy to hear that I'm almost through talking. but I'm going to introduce Anand now and go through his bio. So I've put it down here myself. So what's kind of neat is he started with Shell in 2007 as a seismic geophysicist. You know, that's almost an anathema, but that's okay. In 2010, he went into the Scripps Institute in San Diego, where he was studying marine electromagnetics. And he finished his PhD in 2014, where he focused on, as we read here, uncertainty estimation in electromagnetic inversion for marine hydrocarbon exploration. And then he went into the oil and gas, and he worked for Chevron R&D from 2012 until quite recently, just last year, where he did things like CSEM and FWI, which are usually they're not really that well connected, so that's pretty cool. Reservoir properties from seismic, maybe we can call that QI. AEM and statistical hydrocarbon exploration look-back analyses. So you can see he's quite interested in the statistical side, and machine learning, which is now a big buzzword. And his question is, how credibly can we interpret our inversion models? And so with the advent of HPC, high performance computing, you can really start trying to get a better handle on all of that. Now, right now, he's co-advising a PhD student in Columbia University on Bayesian geophysical inversion. That's going to be something quite similar to the topic we have today. And he's been active in convening and organizing the Uncertainty in Geophysical Inversion session at the AGU. Doubt this year he'll be going there. But at any rate, yeah. In just March last year, he joined Geoscience Australia. And so he's way the heck out there on the East Coast in Canberra. And he continues to work on inverse uncertainty, model representation, and geostatistics. So with that, I'm going to stop sharing my screen, and we'll let Anand go ahead and give his talk, and I'm going to mute myself for now.
Thanks, Todd. Let me get the share screen part, and let's see, let's share desktop 1, which is where we should, with some luck, be able to. Okay, so here we are. So we're going to talk about seismic FWI today, and you know, on the face of it, it would appear that it's not very similar to controlled source electromagnetics. But bear with me, I hope to be able to show you the similarities. In fact, there's lots of similarities from my vantage point, having had the fortune of worked across a lot of geophysics, that all of these inverse problems have some elements in common. And so I'm always hesitant to tell someone, oh, well, you know, they're working in that field, they're an MT expert, and they possibly couldn't help me with my problem to do with tomography. It's surprising how much overlap there is. And so this was work that was done about 5 years ago when I was working at Chevron. So I'll have to acknowledge my coworkers there. Sam Kaplan, John Washburn, Uwe, Anusha, Mike Hoverstein, all really great people. And, you know, some of them are great at software, some of them are great at theoretical physics, some are just, they've been hacking away at this really hard problem for about 15 years now. So they all bring different things to the table, and I'm rather proud of this work that I'm going to present. And when we tried to get, after having proved the concept in 1D, we tried then to move on to 2D. And for that, I've got to acknowledge Reese Hawkins and Malcolm Sambridge, who were at ANU at the time, who really provided quite a lot of guidance on how that could be done. So without further ado, though this is not what I'm working on currently, it's still very relevant. And I think given the number of citations I see to do with FWI and the number of papers coming out, it is a very hot topic. In fact, one might even say that it is the holy grail of exploration geophysics, if we could solve seismic full waveform inversion and make no approximations. So diving right into, the problem with seismic FWI is that if you look at this equation, I don't have too many of them, so don't worry about that. And if I do, they're all in really large, comfortable letters, so don't worry. If you look at the right-hand side of this equation, the first term is what is known to everybody as the data misfit term. And you can weight that misfit, which is d minus f of m, where m is your velocity model, which you propagate through a forward operator, that's f. And then you've got the data d. And what you're basically doing is, subtracting one from the other, you get the residuals, you weight them by the data noise, hopefully, and then you've got the data misfit term. And then you've got to have some appropriate measure of how complicated your model is. And that's the second term on the right. And that's, you balance the two with this lambda square term, a positive scalar. And so then you've got your misfit term, you've got your model norm term, and then you've got to try to make sure that you're not overfitting the data by balancing with the, how complicated the model is, or the model complexity. And that's done using this trade-off parameter known as lambda. And these are just variants of what's known as Tikhonov's regularization, which has been around for many years, but it's hard to do properly. And there's many philosophies around doing it. And so you want the minimum of this objective function. And if you were to solve it deterministically, as all these problems you run into, you'll have to select some operator R, which acts on your model to keep it simple. And then there's a whole plethora of operators to choose from. So what is ideal? The solution requires some form of linearization. So you solve a nonlinear step to get the misfit. And then you've got to do a linearization to then take a step in the direction of the gradient that gets you towards the minimum. Which can be complicated. Finding these gradients and linearizing is not always easy. In fact, we've got a talk, it seems, by Anandaroop Ray in a few weeks to talk about this very issue. Machine learning seems to offer quite a few exciting possibilities of doing this easily. Then there's also lots of local misfit minima. And so it's hard to know once you've reached something which is a minimum of the difference between the data and the computation and the prediction. Is that the right minimum of the velocity model? Is that the image you're looking for? And then you're not sure if you've converged. And finally, and this comes back to the R operator, you've got to limit the complexity of your model, and the model is high dimensional. And so all of these aspects of the problem make it very hard to solve. So if you've got a Bayesian approach instead, you can appeal to parsimony, which is what I'll be talking about. You don't necessarily need to linearize. You can do all these parallel methods to ensure that you're not trapped in a local minimum, because you've got one set of computations talking to another set of computations, and then there's this talk in between them to basically pull someone that's stuck in a misfit minimum into a place that's not a misfit minimum. And I won't talk in detail about that, but I'll touch upon it. There are convergence guarantees for Markov chain Monte Carlo, though they're a bit of a theoretical construct, because you really need to sample for a very long time. And if you've got till the age of the universe, you are guaranteed to converge, but you don't have that much time. But again, you can appeal to parsimony, you can reduce the model dimension, you can make the problem better behaved. And so what I found is that you can put in a lot of expense into getting one solution using deterministic methods, or you can put in similar amounts of expense into getting, shall we say, slightly less high fidelity, but more certain models using Bayesian methods. So again, that's very abstract. So once I show you a few images, perhaps that will become clear. And I'm going to turn down the heating a little bit, because my house is kind of cold and the temperature setting can be a little wonky, so don't go anywhere. I'm back. Yeah, so there is a traditional Bayesian view, which is fairly similar to the deterministic view, and I'll show you how that is. So whenever, I used to look at Bayes' theorem more than a decade ago, my eyes used to gloss over and I used to faint because, what are all these bars going from left to right and given? But really, it's not that hard. We're doing it all the time. Just read it from right to left. M is your velocity model. It comes from, prior experience of having drilled someplace, having done imaging, but it has to be independent. This prior knowledge of your velocity that you're searching for has to be independent of the data. Loosely speaking, we'll get to that. So that's your prior probability. Now, if you travel to the next box to the left, that's your likelihood. So what that is essentially a measure, a probabilistic measure of how accurate your prediction of the observations are. So how well have you been able to match the data? And then once you've weighted your prior assumptions with how well those assumptions hold up to the data, you now have a posterior belief in that velocity model. So now you switch the D and M. So on the right-hand side, you have the prior knowledge, you then sample the model, you saw how it fit the data, you reweighted your prior belief on that basis, and on the left-hand side, now you have a posterior belief in that velocity model. So it's really no more complicated than that. I came to Canberra a year ago. I was a little hesitant about what kind of city Canberra was. You don't hear too much about Canberra in the US. So I had these prior notions of Canberra, but I was broad-minded enough to believe that it's a great place to live in. And, as I've been here over a year, I mean, the likelihood of that, it being a great place to live in has increased. So now I have a posterior belief which says that Canberra is a great place to live in. So we're doing it all the time. It's not that complicated. Bayes' theorem is really no more difficult than that. There is an equivalence with optimization. So I've drawn the arrows which show you what those equivalences are. Your prior model, and depending on how you parameterize it, what kind of covariances you might want to use or measures of complexity, it is equivalent to a model norm. The likelihood is equivalent to your data misfit, and your posterior probability. I mean, if it was a nicely behaved problem with just one minimum, the minimum of your misfit function or your objective function would be the maximum of the posterior probability. However, because of all those annoying things that I mentioned earlier, especially the non-linearity of the problem, how there's local minima, and these things go hand in hand, it's really more of a theoretical comfort. Because anyone who's worked with FWI knows about cycle skips, and we will get to that. So one of the things that I've been single-mindedly going after over the last nearly a decade now, and is this method called trans-dimensional Bayesian inversion. And that's something that Malcolm Sambridge and co. And Alberto Malinverno at Lamont have really popularized, and they've brought this very useful statistical method, which is derived from reversible jump Markov chain Monte Carlo to geophysics. And you've shown us how useful it is, where you do more than just find uncertainties on values of velocity. You also find uncertainties on the complexity of the image or the velocity model in question. And that really, it does both things. It's able to fit your data, and it's also able to give you an explicable idea of what that complexity is. It's not objective, because remember, in Bayesian inversion, there is no such thing as objective Bayesian inversion, because there is a prior. What prior you select is up to you, so it is subjective. However, you have to defend your choice of prior. Once you've selected a family of prior velocity models, and how many layers or nuclei or wavelet coefficients you're going to parameterize them with, trans-D methods give you the ability to simultaneously fit the data as well as penalized complexity, which are the two terms you see in this equation over here. K is the number of parameters you need to explain the data after you've done the experiment. That's on your left-hand side. So given the data, how many parameters do I need to explain the data? And on the right-hand side, the first term, which is the PD given a K parameter velocity model, that's basically the likelihood of your data fit of a K parameter data model. So as you know, well, the fit gets better the more parameters I use. But if you've got the right noise statistics, after a certain point of increasing the complexity of the model, the likelihood doesn't increase any further. So the likelihood kind of, the misfit decreases, the likelihood increases because low misfit is high likelihood. So the high likelihood asymptotes. And then after that, if you keep adding parameters, you're basically multiplying fractions into each other. And if you multiply a whole lot of fractions less than 1 into each other, you're going to get 0. So you automatically see, built into Bayes' theorem in a transduce formulation, this balancing of the model complexity, which is that F1 times F2 times F to the K with the likelihood term. And this is really neat. You don't have to formulate anything differently. It's just intrinsic to Bayes and model selection. So let's get to some data. So this is, so first of all the images and data that I'm going to be showing today are from 2 papers that we published while at Chevron. So you can actually go and get all these images from Geophysical Journal International website. You might find it on my website as well. So on the left-hand side, this is some really interesting data collected in the late 90s, early 2000s in the North Sea. And so all of this that you're seeing now is representative of the geophysical situation 20 years ago. So it has no bearing whatsoever on the current state of the reservoir today. And this is an important thing to note because right now there's been 20 years of production. So all the images you're looking at, all the inferences that we're making, they're just for theoretical purposes of discussing, and you can find them all in the paper that's been published. I'll mention at the end. So on the left, you've got this ocean bottom cable shot data in very shallow water. And this is a difficult problem because you've got your source, you've got the receivers on the ocean bottom. So the moment you've got your direct wave hitting your source, I mean, the direct wave train is still, ringing when you've got reflections and refractions from the Earth. And so it's beautiful data, but there's a lot of interference. If you look at this data, you can see the direct wave, you can see multiples, you can also see diving waves going off over there. And these hyperbolic things are, well, the reflections. And there's some really, steep slope events which are very slow, and we'll talk about those. And if you take every trace and you Fourier transform it, well, I've drawn you the amplitude spectrum on the right-hand side, and these inversions have been done in the frequency domain. So you've basically got the wave equation, you take the Fourier transform, you get the Helmholtz equation, and then instead of solving the wave equation, we're solving the frequency domain wave equation, the Helmholtz equation. And so for that, the data are in the frequency domain, which are to your right. And I think, well, you can see that you basically got a lot of power up to about 100 and something hertz. And most of the power really is concentrated well below 50 hertz. And so because we had limited computational capacity, I think we just took some 10 or 18 frequencies. We will find out in the next slide. And in the high power regions, which correspond to the red. And so we have these, you're probably not used to seeing seismic data this way. And this is where the equivalence with controlled source electromagnetics comes in. You're going to look at amplitude versus offset in the frequency domain. So yeah, these rows are self-explanatory. They're just parts of the image that you saw on the last slide. If I take a line through each of them, then I can draw a profile, and then you end up with these beautiful images of seismic data at different frequencies, 18 frequencies selected every 0.5 hertz. Each frequency represented in a different color in the third row. And yeah, so you can see some nice notches, probably corresponding to wave guiding and all kinds of interference. And then because this is real data, we've got this ripple effect, and there's not really much you can do about that. So it's just, data is just data. You've got to live with it. And if, for those of you who are familiar with controlled source electromagnetics, this is exactly what an amplitude versus offset curve looks like, you know, for frequency domain electromagnetic data. And so yeah, there's all these parallels, even though the physics of CSEM is slightly different, it's diffusion. And here, before I show anyone any results, I'd like to know, well, have you been able to fit the data? So we've got 18 boxes here, I think. 1, 2, 3, 4, 5, 6. Yes, 6 times 3, that's 18 boxes. Each box corresponds to a particular frequency. On the x-axis is offset, and on the y-axis is just pressure normalized to the maximum pressure at 0 offset, I believe, and in decibels. And so the data, you can see the little dinosaur-backed, the little ridges of data, because there's this correlated noise in it, which we can't do anything about. That's in black. And at every frequency, you can see 50 random or 500 random model responses. So if we go to the top left and we look at 5 hertz, you can see that close to you know, 0 offset. And this is another thing. There is no such thing as 0 offset with seismic data. It's a processing construct. When you record data, your streamers are a certain distance away from your explosive source, right? Your compressive source. So I think we started from about 500 meters or so. So close to 0 offset, you know, we're able to fit the data fairly well. And then the further away we go, well, we're not able to fit, I mean, we're still fitting the data, but then the spread of data increases. And you'd expect that, right? Because the further away you go, the SNR decreases, signal to noise, and so, you know, there will be a greater spread. Also, these signals are probably coming from deeper in the earth. So it's a very nice representation of what really goes on in the earth. And what's very cool is as you go from top left to bottom right, you're increasing in frequency content. And surely enough, you can see the notches beginning to you know, show up. So the high frequency content of the data is beginning to show up. And right till about 13 hertz, except the, you know, the correlated wiggle that you see, which is, you know, there's, we can't do anything about the little ripple that you see in the data. That's probably, you know, a processing or recording artifact. So this is basically fresh off the boat. This is raw data from 20 years ago. There's no processing that's been done to it. No corrections, nothing. It's just data as is data. And we're able to even match all the notches in the data. So right until 13.5 hertz, where I guess, you know, it's too high frequency and we're not able to match the later offset well. But it's really nice because we haven't done anything to the data. We haven't massaged the data. We haven't used any processing tricks. This is just the Helmholtz equation. And solutions to the Helmholtz equation as found via this trans-D sampling, and such a great fit. You know, this is really something that you won't see very often. So how do we do this? So we sampled a model, which this was a layered Earth formulation because the North Sea is really flat at this point. And then so we formulated it in terms of depth to a particular reflector, you know, velocities in between those every reflecting interface, Poisson's model, Poisson's ratio, density, and we also had to take attenuation into account. And this is very important because if you don't take attenuation into account, and this is something that John Washburn taught me, you kind of learn by accident. I was looking at his jobs in the HPC queue, and they had like different values of Q associated with them. And I was like, maybe I should be inverting for Q. And what do you know? If we don't invert for Q, it's very hard to actually be able to match your data to your computations, the F of M, because if you don't incorporate Q, things will be so ringy that the misfit space will become almost impossible to descend. So that's our model formulation. So basically interfaces, velocity, Poisson's ratio, density, QP, and QS. So that one Q factor for compressional and another for shear. So you've got to compute the Green function, which is G. So what that is without the wavelet, what is the reflectivity response of the Earth? And because we're in the Fourier domain, we know in the time domain that your source wavelet involved with your Green function is the data. Right? I mean, and this is true for any linear partial differential equation because of, well, linearity. Well, since you've got this convolution in the time domain, it's just a multiplication of the frequency domain. So you take your Green's function in the frequency domain, just multiply it into something, and you should be able to get the data. And that's just a linear problem. So what you do is you get a least squares estimate of the wavelet, or you can derive it as a maximum likelihood estimation of the wavelet at every frequency, where L is the frequency in question. And it looks complicated, but it's not. It's no more complicated than what I said. And once you've got that wavelet estimate for a particular velocity model, for model M, you just multiply that into your Green's function for that model again, and that gives you your computation. And then you do a little more math, and then you get this maximum likelihood objective function, which is basically your misfit. This is your WD minus F of M. In this, what we've done is also, we've estimated the data noise. So in one fell swoop, we've estimated the source wavelet, we've estimated the data noise per frequency. And this is something the geoacoustics guys have been doing for the longest time. So the first I ever heard of this was by Gerstoft and Mecklenbraucher, I think from 2000. And so yeah, it's again, a really cool formulation because the things you don't know, you're not assuming over here. You're saying, I don't know the source wavelet, I don't know the noise, and you're solving for them as a function of the model. So you don't have to sample them. You just sample the model and you get these things kind of for free. And that helps you calculate your misfit. And then we arrive at the part that all the exploration managers are interested in. Well, so what do you have to say about velocity in the Earth? So some of you might not be familiar with these plots. Darker colors correspond to higher probability. So what we've got is on the y-axis, we've got depth. And on the x-axis, we've got whatever property we're inverting for. So in our case, that was VP, V shear, density, QP, and the quality factor for the shear waves. And over here on the right-hand side is a histogram of where the algorithm wants to put in interfaces in the Earth. And this is where Todd's right. It begins to get very different from controlled source electromagnetics, because if someone can show me this kind of resolution for controlled source electromagnetics at 2.5 kilometers depth, I will not believe them, simply because it's diffusive physics. So look at how sharp these changes are, right? And look at how narrow these bounds are. So between the blue lines at every depth, if we look at the velocity, that's the first column to your left. If we look at the compressional velocity, between the blue lines is where 90% of the inverted models lie. And so when you're close to the surface, there's nearly no uncertainty. And then as you get deeper and you get deeper, that's when the envelope of that 90% of inverted models expands, as you'd expect, because uncertainty should go up as you get looking deeper into the Earth. You have something similar for the shear velocities as well. And density we know is not so well resolved. So I almost like to think of density as a nuisance parameter, but if you don't have it there, you will you'll trade off the VP and the VS. And it's the same with the Q factor. You know, there's various different kinds of physics you can use for Q. I'm not sure what Chevron uses here, but I think it's not too different from what Brian Kennett used in his Kennett reflectivity paper from, I think, back in the 70s or late 70s. So yeah, you can see that VP and VS are fairly well resolved up to 2 kilometers depth. Density, not so well, but again, it's necessary to have in QP and QS, which if you don't have, you're just not going to get sensible results. Let's see, I also have these lines over here, which correspond to two unconformities at these depths. I don't remember their names anymore, but wherever you have these unconformities, especially the one at 1500 meters depth, you see that there's quite a spike in the algorithm wanting to put an interface. So here again is using the methodology that I just prescribed. We've got in the column to the top, in the box to the top right, we've got the sampled wavelet. So this was not the wavelet which was given to us. This is the wavelet which was inferred from our inversion process during the inversion. And this was the smooth wavelet which was provided to us. And so we were given what's known as a far field signature. And it's basically a recording of, you know, the shot as it goes off. And you can see that the two don't match. And so our guess is it's hard to know with things like the far field signature from 1998 or 2000 or whenever the survey was carried out, you know, what was the processing applied to it? Because the data we know is raw, but was something done to the far field signature? Is that really the wavelet? We don't know. And there's a lot of, you know, there can be some differences between line to line and shot to shot. And so it's good if you can invert for the wavelet and not make any assumptions about the wavelet. And you can see that they're not the same. And had we used the wavelet provided, we'd have been biasing our inversion to, you know, give us different velocity values because all these things trade off. So it's really cool that, you know, we've been able to estimate the wavelet, which kind of looks like the wavelet provided, but not. The other thing about transdimensional inversion that I mentioned was, you know, it automatically penalizes or regulates the complexity. And we never needed more than, I mean, the maximum number of interfaces or reflectors that we need seems to be around 40 or so, which is reasonable. We don't have to over parameterize the Earth with 200 layers to be able to figure out what's going on in the Earth. And here are some of the, these are some of the plots that in the FWI world are known as butterfly plots, well, for obvious reasons. Okay, I'd like to ask the audience a question here. So can anyone tell me, one side is data, and the other side is the prediction, but it's not very clear to me which is which. I know the answer, but can anyone tell me which is which? And this is why I guess you know, online meetings. I don't know quite how to do this. To do a poll from the audience. Apparently there are ways to do this. So when I get better at it, you know, is there someone in chat saying anything? Does anyone know what the no, I don't see any question. Oh, well, there's something in the chat. Yeah, there we are. Okay. Yes. So we do have some fairly astute observers, and hopefully that's not because I was pointing towards. That's fine. But you're exactly right. So I see that people say that data is on the left, and you're absolutely right, Roman. That is because the right is perfectly noise-free. Yes, that's absolutely right. So if I close this, hopefully it's not gonna remove everything. Okay, so, well, you're absolutely right, because there's noise, there's random noise on the left, whereas on the right, you can see this very regular, you know, you can basically see plane waves in the orthogonal direction. However, where you've got signal, notice how well matched the model data, which is on your right, and the observations on your left are. Notice that the center is not zero offset. It's about 300 meters or so. And again, these are digitizations of the original images. So because I don't have the data anymore, but I think I've been able to do a fairly decent job. You can see here, this is a beautiful image actually. So this is from one of the models in the posterior ensemble that have been inverted. I've forward computed what the seismic data ought to look like. And if you look at, I don't know if you can see my mouse, I'm trying to go between 0.5 and 1 second at about, the first tick away from the central offset. So you can see the water velocity. And remember, this is not two-way time because this is ocean bottom cable receiver. So it's not two-way time. And then you can see the diving waves to the left as well. And so that's the refractions, that's, you can also see the hyperbolic reflections. And this is beautiful because you're matching in amplitude and you're matching in phase. And had I had more time, or had I had the real data, I would have taken the data and then put it on the other side of the model computations. And you would have seen how even on the far offsets, they match very well. The phases and the amplitudes really match. There's been no amplitude gain correction or anything done over here. And this is kind of the dream which Tarantula thought of early 1980s, but it's just been very hard to demonstrate this. I think with this paper, we definitively say you can do this. And because we haven't made any approximations, we just used Bayes' theorem. Now, if we get to the next model, you might have noticed a small shift in your screen. I'll flip back and forth. So there's the uncertainty in your data. So it's, even though you've been able to, within human capability to match, look at them and say, oh, they kind of match very well. There, you did see a slight difference on the right-hand side between the responses of the two models. And that's the uncertainty coming in. So, the models are different. The velocities are fairly different deeper down. So you can see the uncertainty of that in the later times. Also notice some fairly steeply dipping events, which are, the converted mode shear events. So even though we're recording on this is the P-wave data, so this is the hydrophone data, you can still see the, the shear effects. And this is so cool. I mean, it's just very nice when, physics and the theory and inversion comes together like it ought to. And this is the mean from, I think, 100 responses. I just stacked them together. So it's a little brighter than any one individual response. And, it's, again, it fits the data well. And just to, prove to you the point, to hammer the point home that we've been able to match the phases as well. I've basically taken the image and then in MATLAB, I've done some gamma correction and this is what you get. Again, I wish I had the real data, but again, I don't work for Chevron anymore, so, well, I don't have the real data. Yeah, so you can see that the phases match, and I've shown you earlier that the amplitudes match fairly well as well. And again, this is brilliant. You can see reflections, you can see these steep angle things, which are most likely to be shear effects, converted waves. You can see the ringing of the water. You can see the diving waves as well. And so there's all that physics and no processing applied to the data. And so I think, in our quest in industry for realism, we always ignore things that can be derived from first principles, don't use any approximations or minimal approximations like, Kennett's 1979 reflectivity methods. They're full waveform responses, and but unfortunately they're 1D. But there's a lot to be learned from doing these simple experiments in applicable areas with real data and physics that doesn't make any approximations, because you get a lot of intuition and insight into what does work. And so this was really cool, and this just definitively proves that frequency domain, full waveform inversion, does work. And what's very interesting about these plots is you could ask, well, you've done your inversion in the frequency domain, but you're showing me these plots in the time domain. Well, because the velocity model ought to be applicable to all frequencies. So I can compute the Green's function at frequencies I haven't inverted. And then I can inverse Fourier transform the response and then give you the response in time. And that's what I'm doing over here. So I'm showing you the result at frequencies not inverting. And so for all you data science enthusiasts out there, never believe a result unless you look at the predictions outside of where you've inverted the data or where you fit the data. And this is basically that, you know? So I've inverted only 18 frequencies, but I'm showing you very many more to be able to construct a seismogram. And then you could ask, well, how about going to 2D? Because all this is great in 1D. You can do it in 2D. And this is where we use this approach that's been popularized by Malcolm Sainsbury and Rees Hawkins. This is a compact version of the Marmousi model. And what I'm showing you here is that with just 2 shots, Gauss-Newton was completely unable to update the model. And then you'll say, well, that's only using 2 shots. That's not surprising. And did you use, what is the term? There's some kind of image compensation that you can do. And, did you do that? No, we didn't. However, 2 shots, you know you're going to get a garbage result. You're going to get a garbage image. As in Gauss-Newton wasn't even able to, you know, make 1 step. Now, with these trans-D methods, where you parameterize instead of using layers, you use wavelet coefficients, you know, in 200 iterations, you get some ridiculous idea of what the background velocities are like. By 5,000 iterations, you've got a better idea. And then, well, you iterate, and then, yeah, you know, this is the best you could hope to do given the model that we fed it. And this was what we iterated at iteration 1 million. And so this is where, you know, it always amazes me that these nonlinear problems, they're very hard to solve, but you don't need a whole lot of data to be able to get sensible results. And I think this is not appreciated enough, or not, well, again, this is my suspicion. I could be completely wrong about this. But I think we come from an imaging perspective, and we think the more data we have, the better. But first of all, the more data we have, you've got to do things to be able to invert all that data. Handling all that data is not easy. You spend a lot of your HPC time just manipulating the data. Whereas over here, with just 2 shots, we're able to give you some decent idea of what the background velocities and even some of the reflectors are. And I think we went up to only 3 Hertz or something. So what that means is that if you have less data, your posterior can be, you know, it can have all these holes and multiple minima, but should you be able to punch through them, as you can do with some of these sampling methods, you can get, with not much computation, you can get a decent idea of what you're trying to infer. And this is because of the nonlinearities, not in spite of, but because of the nonlinearities. The nonlinearities make your problem more informative. They also make it more difficult to solve, but they make your problem more informative. With just 2 shots, we can say a whole lot. This is just a plot of the number of coefficients we needed, wavelet transform, never needed more than 450. And you aren't limited to using the wavelet transform. So if you go to my website, you'll see that we've been using these methods known as Gaussian processes as well, which in my opinion, do away with some of the difficulties of using wavelet transforms because they're not intuitive. But I think the wavelet transform method shows us that there are ways in which to parameterize 2D or 3D problems and sample them using the theory of transdimensional sampling and get reasonable results. And here's a mean model from the trans-D result on your right, and here's the true model that we actually fed the data. And you know, if you step away and squint a little bit, because this is at 2.5 Hertz or something, you know, the match isn't bad. And there's uncertainty involved. So the mean model, especially for a nonlinear problem, is you know, it's not much of anything. So you can see again, as before, you can see uncertainties, whether in slice or traverse or section view. I forget what these things are called. Map view, plan view. So again, darker colors correspond to higher probabilities. The red line is the true velocity, and the same as with 1D. And why should it be any different in 2D if you're following physics, right? You can see that up shallow, your uncertainty is low. Down deeper, your uncertainty is higher. This is, you know, in the middle when you're far away from the shots, that's where the uncertainty increases. And so, you know, all of this is great stuff. And this is directly from the paper, which is why I show it. Yeah, so you've got basically your two shots, and you see the butterfly plots over here. And because this is synthetic data, there was noise added, but you can basically see how well you're able to match all the kinematics, the AVO signatures. It's all good. And so I'll leave you at that. Seismic inversion is not AVA inversion. You know, I mean, AVA inversion happens after migration. There's a whole lot of assumptions made. We can do better than that. Non-linearity is useful, though difficult to handle. And you can use stochastic methods or other methods that you know, I think Malcolm Sanders has recently been looking at to be able to tell, or to be able to try and invert with reduced complexity and yet be able to fit the data to provide informative answers. And so if you've got less data and a nonlinear problem, you'll be surprised as to how much information you can tease out of the earth. And if you want to read more about what I presented in today's presentation, please have a look at these papers to the right. And I think I will leave you with that. Thank you.
All right, well, thanks a lot. There's some clapping going on in the chat room.
Oh, excellent, excellent.
We'll put slowly, my guy will come back. Now, in terms of, I don't see any questions. I'd say if people have any questions or ideas, maybe pop in and type them in the Q&A area, and we'll get to them. Malcolm has raised his hand, but let's try a little bit of typing here. Instead of raising your hands, just go down to the Q&A spot and type in, please. Let's see. Right. So there were some hand raised, but nobody typing any questions in. Well, for me, just a quick one, just to make sure that I'm catching. Now, when you made your synthetics against the data, you know, those butterfly displays, I'm assuming you used the wave equation forward modeling from your model, and like the kind of the standard approach using your, I guess, your synthetic wavelet and pumped it through, right?
Yes and no.
Yeah, that's a question because, so, you know, the standard FWI, when people are feverishly checking their results, they will compare a forward modeling that is generated from the model using a kind of a quick and dirty wave equation modeling.
Yeah, so I think the best way to answer that is we've got a velocity model. I've got a bunch of inverted velocity models. For every velocity model, at every frequency, I can get a source wavelet. I can estimate a source wavelet. That's through that, you know, maximum likelihood estimation technique I talked about. So with that source wavelet, given the data and a velocity model, I can estimate a source wavelet. Mm-hmm. Given the velocity model and the source wavelet at every frequency, I can compute what the response ought to be in the frequency domain. So that's using a Helmholtz solver. So the solutions to the Helmholtz equation. And then, since that's in the frequency domain, I inverse Fourier transform and then use this idea of conjugate symmetry because it's a real signal. And then I forward calculate so there isn't any forward calculation in the time domain done. It's all in the frequency domain, including if frequency is not inverted, because I can estimate a wavelet at any frequency given the data. And then I put that onto the velocity model Green's function, compute the responses in the frequency domain, then inverse Fourier transform in the into time. And that's what gives you the seismic graph.
Right. So, I mean, that's the nuts and bolts of the program. Now, have you compared your final synthetic with one where you would take your model results of what, you know, like the mean one or the whatever, and compare that with a standard wave equation modeling synthetic that you generate to see?
Oh, yeah. So we've done that. So the modeler has been
Yeah.
compared against, both finite difference simulations as well as, so in the kinetic reflectivity world, actually, there is no such thing as a time domain modeler. You actually do all the modeling in the frequency domain, and then you model it in the time domain with an inverse Fourier transform. So yes, it definitely does match.
Yeah, I mean, literally, if you wanted to compare against a standard FWI result, then you want to be using this same kind of algorithm in the end to, well, in other words, what a lot of people will be using this model for would be to go ahead and do a pre-stack depth migration, say, or, you know, start one up or something. So
this is what we're saying. Like, yes,
yeah.
you could. But the point is, I would encourage people to get away from paradigms like pre-stack depth migration, etc., and try to focus their attentions instead on teasing out the maximum you can from your velocity model. And then, of course, you could use that for migration as the starting velocity, and then do an RTM. But what we're trying to say is that perhaps you don't need to. And
Well,
I know
no,
that's a bold
that's
statement.
the holy grail. It's not great for, say, seismic shops, but you know, but yeah, literally that's why FWI is so popular too, because oil companies are hoping that they can just get some field records and crank it through and get something that the interpreters can use for QI, and of course you could always make a zero offset simple synthetic, you know, in a few seconds from any of these models if they're detailed enough. Let's see if we've got any. Okay, I'm seeing some.
So I know that Malcolm definitely did ask a question. Oh, here we are. Did your illumination of the data covariance matrix assume that it was diagonal and hence that the data noise was independent? Malcolm always asks the hard questions. No, unfortunately, our covariance estimation technique was assumed a diagonal matrix. However, we know the form of the ripple. So it seems to have a constant wavelet. And so if we really wanted to, we could formulate a covariance matrix where we assume a shape of the correlated noise, and then we could invert. But this was the first time that the oil prices crashed in 2014. I know they're bad now, they were bad then. It seems like we've been living in this forever. So we didn't have a whole lot of time to investigate how to, go with, non-diagonal correlation matrices for the noise. But it's entirely possible, as you all know. But we didn't do that, no. But our residuals were Gaussian. So, I mean, the Gaussian approximation was met. Okay, so I see something from Richard Taylor here. Can you clarify the source wavelet estimation a bit more? Is it, so Richard, well, for the benefit of those who don't know, Richard Taylor is this bright young physicist at GA who's been working on estimating the noise parameters from the data itself for airborne electromagnetics. We have also estimated the noise parameters from the data for, FWI, because it's just data. Statistics doesn't care. So using a very similar procedure, you know that the Green's function times the wavelet coefficient equals to the data for a particular model that gives you the Green's function. And you don't know that wavelet coefficient, but you know the model and you know the data. So then you can just do the least square solution for the wavelet coefficients from the data. You get those coefficients. You get one coefficient per frequency. You multiply that into your Green's function, forward compute, get the frequency response at a particular frequency, and then the residual with the data is your data residual. It seems like you're double dipping, but you're not. And Ross Costello, why stop at 13.5 hertz? Because it gets incredibly slow, the forward computation, the higher the frequencies you use. I mean, and also you've got to do a Bessel function Hankel transform to compute the response from the wave number to the offset domain. Right. And that integral is very hard to do at higher frequencies. So you could tell that at 13.5 hertz and above, we're not really being able to match the data. So, you know, we just decided that we'll leave it at that. Alexi, is the left the synthetic? Actually, the left was the real data. The synthetic was on the right because, as Roman pointed out, there was random noise on the left. Yeah, but yeah, I mean, that's how confusing it is. Even I look at it and I'm like, oh, which is real, which is not.
Let's see, any more questions we can hunt through here. Malcolm had another, what about quantifying trade-offs with these models? That's a good one.
Sure. Actually, we did quantify trade-offs in the plot that's, you know, actually, if I have a minute, I'll just share my screen again.
Why don't we do that? That'll be great. Yes.
Yeah, I'll just share my screen again, and then hopefully you can see my screen here. Let's move this away. We move away from the pièce de résistance to, so you can see here, I don't know if I can I zoom in using, is it possible to zoom in using, on a Mac? I know you can.
Well, you could go out of show and then just zoom in manually on your slide.
Oh yeah, so let's see. Okay, there we are. Oh, I am on a Mac, so I should just be able to, do that. Right, yeah. There we are. So if you look at 1500 meters, for example, you can see that the VP is kind of bent. So what you're doing is, as the velocities at the interface, if it wants to put the interface deeper, it also gets faster because, you know, that's what gives it the bent shape. Do you see where my mouse is? So that's again essentially the trade-off that you're seeing, because it wants to put an interface close to 1500 meters depth, but if it wants to put it any deeper, it has to go to the right, which is what gives you that slanted line. So there actually are trade-offs. It's just that the scale of the trade-offs is so slow. Because remember, this is mostly reflection data because we're hardly out to 3.5 kilometers. So all the, you know, the diving wave stuff will be very shallow. And so, and that's what's so great about this, because it's, you know, I wouldn't say it's easy, but people have done FWI with diving waves. With reflections is the hard part. And this is mostly a reflection because we haven't gone that far out in offset. And our approximations of 1D wouldn't be valid at that point. And so, yeah, so that answers that, I hope. I've completely lost my screens. Okay, yeah, so I'll stop the share now. Oh, thank you again, Malcolm. Thank you for all the clapping. Not used to that much praise, but well, thank you. It's much appreciated.
And definitely, this was a great talk. A lot of participants and a lot of interest. So we'll have. If there are any more questions, you can definitely either pass it to. You know, myself, for instance, and I'll pass it to Anand, and we will try to sum things up and get back to you on that. All right, so thanks a lot, Anand, and I think it's time for people to go back to work.
Yes, thank you everybody for attending. That's it.
Well, yes, I don't think there's any more questions. No, that's it. Okay, great. All right, thanks now.
All right, bye-bye.
Bye now.
And thanks, Doug, for
hosting
it so wonderfully.
Cheers. That was great. Thanks.